Today we'll discuss about physical properties of alkynes. In this, about state of these these alkynes. The first three members, namely ethyne, propyne and butane, these are gases. Next eight members are in liquid state, while the still higher members, they exist as solids at room temperature. All these are colorless, odorless. Acetylene has slight smell, garlic-like odor. That also is not of acetylene but due to the impurities of phosphine and H2S gas in this compound. About physical constants, the melting and boiling points, they increase gradually with increasing molecular weight. Densities also increase, yet all alkynes are lighter than water. About chemical properties, alkynes contain two pi bonds in them, and as expected, due to the presence of these pi bonds, these are highly reactive compounds and undergo many addition, oxidation and polymerization reaction. One, addition reactions. Addition of hydrogen. Hydrogen adds up in alkynes in presence of nickel, platinum or palladium, giving alkenes. And on further addition of hydrogen to alkenes in the same condition in presence of nickel, palladium or platinum, these get converted into alkanes, the saturated class of compounds. Now, if we want to stop the reaction at alkene stage only, for this hydrogen is added in presence of palladium supported over calcium carbonate, whose catalytic effect is decreased or poisoned by adding lead acetate and quinoline to it, and this reagent is known as Lindlar's catalyst or nickel boride catalyst, which is known as P2, can also be used for the same purpose. Alkynes can also be reduced to alkenes by another method, by treating alkynes with sodium or lithium in presence of liquid ammonia, and the reduction of this type is known as metal ammonia reduction, which is also known as Burke reduction. Now, when the reduction is carried out by metal ammonia reduction or Burke reduction, we get transalkene like this. And in presence of catalytic reduction, hydrogen with palladium supported over calcium carbonate poisoned by lead acetate or quinoline, the alkene formed is cis type of alkene, means syn addition takes place, and by Burke reduction, anti-addition takes place and transalkenes are formed. How the metal ammonia reduction takes place? Let's discuss the mechanism of this reaction. Alkynes in presence of sodium or lithium, whose ionization energies are small and the loosely bound electron can be extracted from these. This electron attacks at triply bonded carbon so that another triply bonded carbon that gets the negative charge and one unpaired electron is on this carbon. So the species is also known as anion radical because negative charge is there as well as unpaired electron is there. So anion radical is formed, and this anion radical, this negative charge on this carbon, this takes up one proton from ammonia NH3, releasing it as amide ion NH2 negative ion RCH. This is the proton which has been accepted from ammonia. Double bond C, R, and C is having one unpaired electron. By taking up another electron from sodium or lithium, this carbon also attains a negative charge and it again abstracts one H positive from ammonia again releasing amide ion, and alkene is formed in turn, and the alkene formed is trans alkene is formed around the C2C double bond. These hydrogens are added in trans manner, anti-addition has taken place. Now coming to electrophilic addition reaction. Those were addition reactions. These electrophilic addition reactions, as alkenes show electrophilic addition reaction because of the presence of one pi bond in them, alkynes are having two pi bonds in them, and it is expected that alkynes should be more reactive towards electrophilic addition reaction because of the presence of two pi bonds in comparison to one pi bond which is present in alkenes. But actually alkynes are less reactive in comparison to alkenes towards electrophilic addition reactions. This unexpected behavior is due to three reasons. One reason is hybridization. Alkynes in which the two carbons are triply bonded, these two carbons are sp hybridized, and in sp hybridization 50% s character is there, means these orbitals are having more s character and s orbitals are more electronegative, and these have lesser effective size. Because of this, the electron pairs in these pi bonds are firmly held in comparison to alkenes where the two carbons are sp2 hybridized, and so are not released very easily towards electrophilic addition reactions. The second reason is cylindrical pi electron cloud. There is greater delocalization of pi electrons as two carbons are having two unhybridized p orbitals having one electron in each orbital. These four lobes above the plane and below the plane, they merge, and the four electrons in these get delocalized. Because of greater delocalization of electrons in alkynes, these are more stable. These are more stable and less reactive. Third factor is stability of intermediate anion. For example, in addition of halogen acid to an alkyne or alkene, halogen acid is HX, which will dissociate to give H positive and X negative. The first step here in both cases will be take up of H positive ion. Alkynes, when take H positive, they form vinyl carbocation. Vinyl, doubly bonded carbon is bearing this positive charge, hence vinyl carbocation. And when H positive is added to alkenes, alkyl carbocation is formed. This carbon which is having positive charge is singly bonded. Now vinylic carbocations, which are formed in case of alkynes by taking up H positive ion, these are less stable than alkyl carbocations which are formed in case of alkenes. Hence, alkynes undergo addition reactions less readily in comparison to alkenes.